Okay, so before we get started, I just wanted to mention something. There's a honor society for engineering technology. It's called Tau Alpha Pi, and I'm actually one of the advisors for it. And I think it's a good if you're eligible. I think it's a good thing to join. There's really not any great commitment that you need to make. But it certainly looks good on your resume. It's basically an honor society. So if you're eligible, I'd say think about it. The eligibility is essentially if you need to have 45 credit hours completed, and you need to have a 3.5. That's basically it. So if you fall into that category, and you have a thought about that, I think it would be a good thing to get into. So with that, so we're going to get into forces a little bit, force analysis, and this should pretty much be a review from other courses you've taken, but nonetheless we'll go through it. But if you have any if I'm going to go through it sort of fast because of that, but if you have questions, jump out and speak up. So essentially what we do in a force analysis is we take a system, which you can see we've got a system here of some sort. It's a hinged structure with a pin in it. And we break that down into segments. You can see sort of taking a chunk of this tubing, square tubing, and looking at it from a segment standpoint, and then finally getting to an element standpoint. And this plays into something we'll spend some time on, being finite element analysis, where you take a structure that you've modeled, impart loads onto it, and all kinds of different loads, and then look at the result that you're going to get in terms of stress in the part, as well as strain. So it's a very useful, very useful tool. And you can use not only mechanical forces, but thermal effects of thermal issues as well. So again, just another example of that. This is again another structure with a tensile force being applied to it, and how does that weigh into the element side. So internal forces, stress, shear, normal forces and shear forces are what we're going to look at, and then the deformations that you get from those. So again, we're going to go through this sort of fast and spend a little bit more time on FEA. This would be fairly typical of a structure, and I'm sure this looks very familiar from statics and dynamics, mechanics maybe. But you've got a hinge member, maybe some sort of crane with a support mechanism on it. You've got a load over a certain area of 4,000 newtons per meter. Sort of the steps you would take if you were going to do this in a sort of a manual kind of methodology. You choose your subsystem, pose an equilibrium condition, replace your distributed load with a concentrated force. This is sort of a simplification, but it's sort of the easiest way to do it. Sum your moments, and then find your ultimate load. So this is stuff you've all done before. Sum your forces in X and Y. It's a two-dimensional system, and basically come up with the stress in the beam. And again, I'm going through this sort of fast, but some similar things here. I'd suggest just take a look at this, make sure you've got your sort of on board with this, and again, it's a review. Again, we're going to focus more on the FEA side than doing the manual kind of systems. But it's the same sort of thing, really, in terms of how you apply loads, simplifications you're going to make, and whatnot. But it's way easier than doing some of this. Again, another example, just summing our forces, summing our moments, assuming an equilibrium condition, and you wind up with the stress and strain in the structure. Again, same sort of thing here, just another example. If we look at stresses, you've got tensile loads, which is where you're trying to pull on something, compressive loads, where you're trying to crush it basically, or putting a load in opposite of tension in compression. And then you've got shear loads, direct shear, you've got vertical shear and beams, which would be the same as torsion, basically, where you're trying to twist something. You've got normal stresses, which are tensile or positive, looked at as positive. The convention is to look at them as positive, or compression to look at as negative. So, and we'll get into that a little bit. We're going to spend quite a bit of time on fatigue, and we'll get into the relationships between tensile and compressive loads there. Stress, just again, very much of a review, is force divided by the area that it's imparted on. Deformation is in strain, again, as our axial load, original length of the loaded member, your modulus, and your cross-sectional area. Pretty simple stuff there. So that's a real quick review. I just wanted to sort of include that in here. And I have a bunch of exercises. You actually have the completed versions of them, so I'm not going to ask you to do them. But take a look at it and make sure that none of it is a foreign object to you. Okay, let me just move this up a little bit. I also included an article, which actually is a couple years old at this point, but it still sort of applies because it's still very much an active area of technology. And it's the use of adhesives. Adhesives have been around forever. Well, I don't know about forever, I guess, but it's really just been some, in fairly recent years, within the last probably 10 years, maybe 15 years, which is sort of recent, used for structural applications. There's been some, probably some of the first applications were in construction, buildings and things like that. And 3M and others were really instrumental in a lot of this. Some of the 3M foam tapes that you can buy at Lowe's now are incredibly strong. And with the using of foam, and we'll talk more about adhesives, I think, next semester. But adhesives, when combined with a substrate like foam, it really increases their usability pretty significantly, because it gives you sort of it ensures that you've got intimate contact between the adhesive and the substrate, okay? Which if you've just got an adhesive, especially a thin layer, think like super glue, right? You need to have two things that you can get in pretty intimate contact. There's not a lot of fill ability if I've got spaces between the two substrates. Foam adhesives foam tape adhesives take care of that. That's one of the things they do, is they provide a little cushion. The other thing is they help a little bit with if I've got vibration issues. And so now you're seeing adhesives used a lot in automobile manufacturing and in just other areas. Aerospace is huge. Airplanes today, especially the composite structure airplanes like the Dreamliner, the Boeing 787, there's a tremendous amount of adhesive in those. And even in some of the aluminum planes, they're using adhesives over rivets. And there's some significant advantages to that. What do you suppose some of them might be? Rivets traditionally were used to put airplanes together. So there was millions, literally millions of rivets in some of the older versions of the 737. And now that's not completely, but a large amount of that has been replaced with adhesive. What do you suppose some of the advantages are? Sorry? Weight, absolutely. What else? Time. Rivets are hard to put in, right? I mean, there's automated ways. They have these Cleco things and all kinds of other automated methods of putting rivets in airplanes, but it still is time consuming. What else?
The price of it.
Yeah, price of it, both in labor and the cost of the rivet. Think from a sort of a structural standpoint. What do rivets need? Need a hole, right? What does a hole do? Potentially do. Creates. Sorry. Well, it potentially creates a stress riser, and so if you've got a structure and it's got a bunch of holes in it, and that is subject to loading, which is a cyclical loading, which most things are, especially in an airplane. It's likely if you're going to get a crack, you're going to get a start at a hole, and we'll talk about that more in fatigue. But that's an issue that adhesives sort of eliminate. Think about again from a loading standpoint. What else do you get with an adhesive that you don't get with a rivet? So where is my load being transferred? What's the area that's being transferred? Just at the rivet, really, if you think about it, right? I have two plates and I put them together. I got 4 rivets, riveting those 2 plates together. Then I try to pull the plates apart. Where's my load concentrated? On the rivets. What if I have an adhesive?
It's distributed along.
Distributed, exactly. That's exactly right. So that's another big advantage of adhesives. So I put this article in here, and what they were talking about was, again, some of the issues that adhesives, and the guy that's the president of Dow, of course, they make adhesives, so he's a little bit skewed. He says it's the new welding, right? Bonding with adhesives is the new welding. And of course, he works for Dow, which makes adhesives. So you might think he would believe that. But one of the other issues, again, I use this example a lot because it's sort of a big design win, maybe, or maybe not, I don't know, depending on which commercials you watch, whether you watch the Ford commercials or the Chevy commercials. But Ford is using aluminum in their, I believe they're still doing it, in the F-150 for their bed. And one of the things that caused was it facilitated, if you will, or it opened the possibility of getting galvanic corrosion, because now I have dissimilar metals, right? I've got aluminum and I got steel, and they will create a galvanic cell between them and cause accelerated corrosion over what you would normally get. And that gets worsened if you're in an environment with salt and water. Okay, so if you're near the ocean, or you're in a climate that gets snow and the roads get salted, that whole galvanic thing sort of goes on steroids. It gets worse. So the way you prevent that is you create an isolation, electrical isolation between the two members, between the aluminum and the steel. What better way to do that than with adhesives, right? Any other method, I'm going to have to insert another part. If I'm going to bolt the bed to the frame, which I think they still do in parts, but they use a lot of adhesives as they're putting things together as well. You can create an automatic barrier, if you will, from galvanic corrosion. So, and again, they're being more used. Typical car today has 27 pounds of adhesives, up from 18 pounds 10 years ago. So that's a pretty significant increase. They increased their market share, if you will, by a factor of 50%. So that's pretty significant when it comes to increasing market share. So you might just take a look at this. Again, they talk about the 787, the fact that it's made of carbon fiber, right? It's a composite structure. Very difficult to, the difficulty with composite structures is putting together and fastening together the individual pieces, right? If you could make the whole airplane out of one huge composite structure, that would be great, but obviously you can't. You need to fasten the wings onto the fuselage, you need to fasten all kinds of things to that fuselage or to the airframe. There's 40 to 50,000 fewer fasteners in that airplane than there is in a conventional aluminum airplane. So that's huge. I don't know what those fasteners cost installed, but I bet you it's a couple dollars, maybe more. The cost of the fastener itself, they're not inexpensive because they're aerospace, or airplane worthy kind of things. And then the big cost is, of course, putting them in. So that's a pretty significant change in the way airplanes are made. Saying that, military airplanes were made out of composites for quite a while, but for a commercial airplane. So again, they're discussing the use in airplane in automobiles, and how they've got some advantages for stiffening. Again, a lot of the foam-based adhesives are very useful. Some places they're not used is typically in high heat applications, so you don't find much in the way of engines, certainly, or even in the engine compartment. So when I take a look at that article when you get a chance, I think it's some useful stuff. Yeah, this was just more review, just looking at some forces on some structures that I put together. I have a couple exercises here, just take a look at them as well. We'll come back to that. Yeah, we'll come back to that too. Okay, just again a little bit more review on some of this stuff. Stress and deformation. This image up above here again is just sort of a relationships, if you will, between external force, internal force, stress, strain, elongation, and finally displacement. So it just gives you sort of a pictorial view of how those are related to each other. And then again, talking about how loads are applied and the forces that you generate. Shear force, this is a good example. You've got a clevis of some sort and held together with a pin, and the shear force that you would generate on that pin, in this case a double shear because it's a double clevis. Again, just the area it acts on, very similar to, till you look at any kind of stress. Would be your force divided by your area it acts on. In the case of shear, it's the area of the pin, right? So it's pretty straightforward kind of stuff. And just some other examples. Single shear, because there's only one shear point on that pin, as opposed to here where you've got double shear or a force acting on both sides. Bearing force, again, another force we look at. Again, it's the force on the bearing and divided by the area that force acts over. We'll talk about bearings next semester. And then torsion, where you're trying to twist something, basically. Right? So again, torsional stress. In the case of torsional stress, you use the polar moment of inertia, not just the direct area. And that's all that is. Twist is important. And then some of the moments or section modulus and moment of inertia, concept of that, how that applies. Again, this should be a review, but just make sure it's something you're got a good understanding of. And then some common shapes. So that it used to be, obviously before FEA, you would try to utilize some of these more common shapes, and you look at Rourke's Handbook of Stress and Strain. That's where most of the stuff was pulled from. There's a huge amount of shapes that you can then use the formulas that they've derived to calculate various characteristics of that system. With the advent of FEA, if you can model it, you can analyze it. That's a lot of that need sort of has gone away. But again, just the different shapes, and these are, again, if you're have a need where you're not going to use or can't use a finite element analysis package, this is useful stuff. Rourke's Handbook of Stress and I think it's Stress and Strain or just Stress, but Rourke's Handbook is a key text. Used to be more so than it is now, but still is useful. But it's got all kinds of different standard kind of loading conditions that you can apply to your designs. So one of the things we're going to spend time on is fatigue. And again, why do you suppose we're going to spend time on fatigue? What do you suppose the percentage of mechanical failures are caused by fatigue? Any idea what that percentage would be? Take a guess. 80? 80? You're close. It's actually 90. Yeah. So 90% of mechanical failures are caused by fatigue. And that's a fairly well accepted number. You might find 80% somewhere, 70%, but it's a huge percentage. Overwhelming majority of failures are caused by that. Why do you suppose that is? Well, because it's really pretty easy to do this kind of stuff, right? Pretty straightforward. Real easy now with FEA, assuming you apply it right. You've got your loading conditions correct, and you did a good model. Very easy to calculate loads for load, just looking at stress, right? I can easily calculate what the stress is in my structure. I can easily calculate what my safety factor is going to be because I know what my yield strength is. Well defined, well understood. Fatigue comes into play because it's a cyclical process, and we will do some analysis of that too using FEA, and that's helped things a little bit. But it's much harder to understand. And one of the issues that comes into play is, well, there's a couple issues. One of the issues is the concept of stress concentration factors. And that's where the maximum stress exceeds the nominal stress. If I'm calculating the stress, say this is a shaft and that's a little turned down portion of the shaft, I can easily calculate, right, all the loads in here, correct? But what am I really calculating? Am I calculating the maximum load or the maximum stress, or am I calculating average stress? What you're calculating is average stress. It's not maximum stress. And what stress concentration factors do is they don't increase the average stress on a structure. If I'm looking at this as a shaft with a turned down portion to it, and maybe that's loaded, maybe this thing goes into here and gets loaded in some way, right? And I calculate what the stress will be in that shaft. It's the average stress I'm calculating. But it's not uniform in a structure of any sort. You're assuming it is, but it's not. What it really is you've got areas of high stress and areas of low stress with an average stress of whatever you've calculated. And those areas of high stress are areas typically where you've got rapid section change or sharp corners. Sharp internal corners are disastrous. That's where you're going to get maximum stress. And we will calculate this. It really becomes apparent when you do a finite element analysis, because you've got, and unfortunately I don't have SolidWorks on this computer. I need to bring my other computer to do that. But you'll see areas, like if that would be a high stress area, and you'll see using color, like all analysis packages typically do, it'll show the areas of the high stress, and that's where you're going to get likely to get fatigue failures initiated. That's where fatigue failures initiate. Fatigue typically, it's a fascinating topic to me. I really, if I was going to be an analysis person, that's what I would want to focus on. But typically in fatigue failures, or always really, you get an initiation point, typically a sharp corner, and a crack initiates. And then that crack grows, and then ultimately you get failure. And I've got some examples when we get into the that section where you've got 70-80% of the material no longer connected to each other, where you'll have a shaft and you'll have a crack that extends 70% of the way through the structure, and yet it's still operating, meaning that they way over designed in terms of average stress. They've got a safety factor of enormous safety factor, 10 or 20, right? But the fatigue is what actually caused the failure. And when that failure occurs in a fatigue situation, typically it's catastrophic. I mean, it's instant and it's just things let go, right? So, but again, the stress concentration factor, that is caused typically by geometry, by feature, where you've got maximum stress exceeding the nominal stress, okay, or the average stress. It's a very local phenomenon. Again, it's typically connected to a geometric discontinuity of some sort, being a sharp corner, being an inclusion and a forging, being lots of things that can cause issues. You need to look at the entire component. We do that in finite element analysis to see where those maximum stress areas lie. And then what do you do when you find one? How do you fix that? Redesign it. Yeah, you need to get the sharp corners out. That's what it comes down to. If you've got manufacturing issues, that's another case. And that's what I'm showing here. This is two plates welded together, fillet weld. Does it actually look like this all the time? Nice weld, nice rounded to it. What are these things? Anybody ever weld anything? What happens when you get a little bit too much amperage, or you hold the torch there a little bit too long? You'll wind up with an undercut, where you've actually burned into the base metal a little bit. That is a great place for fatigue to occur, because again, I've created a sharp corner. So manufacturing can end up causing a lot of fatigue failures, and that's the example I'm showing here too. is that if I'm doing machining and I'm going to turn this little shaft, this little portion of a shaft onto the main body of this thing, and the print calls out a radius here, right? Is that radius easy for me to put on? If I'm on a manual lathe, if I'm on a CNC lathe, it's easy. I just program the radius. If I'm on a manual lathe, is that easy to do? It's really not, because I probably can't turn this shaft with a really large radius tool like that, right? Just generates too much force, too much pressure. I'll get chatter, I won't get dimensional stability. So, you know what I'm going to do? I know this thing fits into this. In fact, I'm making this whole thing. So you know what I'm going to do? I'm going to go ahead and I'm just going to put a little undercut in there. It won't hurt anything, right? Thinks the manufacturing person. But in reality, it does. It creates a sharp corner. That would be a point of fatigue failure. It would initiate, right? So manufacturing can cause a lot of, poor manufacturing practice, I should say, can cause a lot of places where you can wind up with stress concentration factors. Places like this where I've got a weld, I get some undercut, and causes an issue. So so obviously we need to design around a lot of this stuff, and just some of the guidelines for stress concentration factors. Brittle materials are much more problematic than ductile materials. So we talked about A36, right? We talked about A36 steel. Why do you want to use A36? Again, if I've got loading such that I'm well under the yield strength, I'm happy with the modulus that I get with steel, why do I want to use A36? Again, another reason. It's very, very stable when it comes to stress concentration factors. They don't have as big an impact as more brittle materials. If I take a piece of 1040, say, carbon steel, and I heat treat it, have I made it more brittle? Absolutely, right? Ductility goes down as strength goes up. Typically, ductility goes down. If I take a piece of material and I heat treat it, my elongation, which is my measure of ductility, probably drops in half. Maybe my yield strength maybe bumps up, I don't know, 30 KSI maybe, something like that, but my ductility probably drops in half. So I've made that material more prone to fatigue failures because stress concentration factors have a much bigger impact on more brittle materials. Okay? And that is because you get a crack initiation easier with brittle materials. It's sort of intuitive, really. But local deformation, if the material's not ductile enough, causes a fracture. That fracture then propagates and ultimately causes a failure. So if I've got very ductile materials, again, like A36, I've got a static tensile loading situation, then I don't really need to worry about fatigue very much, and I don't need to worry about stress concentration factors as much. A couple of reasons for that. One, if I've got a static tensile loading, to get fatigue, I need to have a cyclical loading. Okay, if I'm just pulling on something, I'll never get a fatigue failure. Or if I'm just pushing on something, I'll never get a fatigue failure. It's where you've got a cyclical loading where you've got tension and compression is the worst case. Or even just varying tension. You'll wind up with the potential, at least, for fatigue failures. And again, under compressive loading, not as big of a factor. The tensile component needs to be there really to get have significant issues with fatigue and stress concentration. I'll come back to that. So if I've got stress concentration factors in areas of cyclical tensile stress, especially with brittle materials, that's where fatigue failures are going to initiate, and that's where I need to focus my time. And again, a stress concentration factor is an abrupt change in geometry. So that's the example would be a sharp corner or a notch. Okay, so the things we look at, and again, a lot of this stuff was developed before FEA, so there was tables that were developed and notch characteristic tables that were developed, again in Rorke's, that you could apply to your design. So based on the characteristics of the notch, typically how sharp it is, okay, if I've got a little radius or the shape of it, there was factors that could be applied, and I think I go through them a little bit, to basically lower your basically lower your design loading to account for that factor. So there are like correction factors that would be applied to your design loading based on the notch characteristics. Today, though, with proper modeling, and that's a key point, with proper modeling, you can model that actual design and then do a fatigue FEA on it, and we'll spend some time doing that. But proper modeling is key, and what comes into play. Have you ever seen FEA? You guys ever played with it at all in SolidWorks or Inventor? But basically, what you're doing is you mesh the product, right, and then the computer. The algorithm basically calculates stress and strain on each little element, each little node that you've created, okay? Then it combines it all together and gives you a stress distribution and strain distribution for the structure, okay? That meshing is key because the more mesh, the tighter your mesh is, the more elements you have. The more elements you have, the slower your analysis is, to the point where your computer just, gives out after 3 or 4 hours, right, of trying to do the calculations, especially a Windows-based machine. So the sort of the default is, well, let me make my mesh a little bit less fine, make it coarser, get less elements, less computation time within the computer, especially, if you look back even 5 years when typically you're running it on a machine that wasn't necessarily all that fast. The problem is, what are we looking at here? Stress concentration factors, things like notches, right? You can get to the point where your notch is sort of invisible to your meshing because it's buried in a node somewhere. You don't have enough. Your meshing is not fine enough. And we'll do some of that where you tighten up your mesh and all of a sudden you wind up with a load that you didn't see before, or not a load, but a stress that you didn't see before because your meshing was too coarse. So proper meshing is key. Not just with fatigue, but with any aspect of doing an FEA. Okay, so here's an example. What do you suppose this is all about? Take a look at those windows. You notice something strange about those?
Square.
They're square. Why do you suppose there's not square windows in airplanes anymore? This is true. This is true. Absolutely true story. I mean, this goes back to the, 50s probably. This is a company called de Havilland, and at the time they were the leading manufacturer. They were the Boeing of the day, if you will. And somebody, didn't really pay that much attention to stress concentration factors, and they made the airplane with square windows. What do you suppose happened to those airplanes? They fell out of the sky. I mean, seriously, like multiple crashes. They went out of business. They no longer are around. So there's your lesson. Don't design an airplane with square windows because you too will go out of business. But seriously, this was a classic example, and it's probably from the 50s. Really the advent of commercial aviation. And for whatever reason, they put square windows in there, and those windows failed. And this is an example. You can't really see the image all that well, but the plane tore apart because it again had a stress concentration factor in the window, had a fairly stressed area of the plane that was seeing cyclical loading and caused failures. So anyway, that's a classic picture. I'm sure everybody that teaches these kind of courses does that. Here's another one. This is a tanker, the Schenectady, that was sitting when it actually failed, was sitting in port. And the ship is now 2 pieces. The back piece and the front piece, busted right in half. And you can see that. It's another classic example of fatigue failure. And again, the thing with fatigue failure is when it occurs, it's catastrophic. It doesn't sort of start to bend, typically. It lets go. And that's the nature of it. And I have some images of fatigue failures that we'll look at that sort of show that. So it's a catastrophic thing. That boat, 1 minute was 1 piece, the next minute was 2 pieces. So nasty stuff. And this gives you a sort of a pictorial example of if you look at stress flow lines within a part, and I've got a rapid section change, okay, sharp corner. The flow lines tend to crowd together, and that's what creates the increase in stress. The average stress through the part doesn't change. Going from this to this doesn't change because my cross section doesn't change. You know, my minimum cross sections don't change. But what does change is how that stress is distributed, and that's how you got to think about it. It's not so because of that, it's not something that I can go with a higher yield strength material and probably have a huge impact on. You can have a little bit of an impact, but you're probably going to lose ductility in doing that, and so you're sort of fighting yourself. The way to fix it is to change that geometric shape and put a fillet in there or a radius in there, so you get a nice smooth flow. Again, I've not done anything to the average stress on this because I haven't changed my cross-sectional area and my loading hasn't changed, but I did distribute my stress better, and that's what it's all about. This is sort of a pictorial view of that, if you will. That's sort of what's happening. So many times, you know, like a lot of things in engineering, you take the wrong approach to solve it. You know, the right approach here is not change my material to something that's got a higher yield strength. Logic might say, well, yeah, that's what I should do, but that's not really correct because again, I'm probably going to get something that's lower ductility as I increase my yield strength, and I'm not going to change the distribution of the stress. And this is just a couple images here, again, of an FEA where you've got a sharp corner here, and this is exactly what you'll see when we do this analysis. Right, you're looking at stress in this case, right? So you've got obviously the blue being the lowest because it's the largest cross-sectional section through the part. The green, again, smaller cross-section, but the area to really worry about again is that sharp corner, which you see here. And you can see the impact of the meshing. If my meshing, and you can sort of see that really well here. If you look, can you guys see that out there? Can you pick out that meshing? See how big the meshing is here? What you do is, to overcome the computational problems, is you mesh fairly large in areas that don't have a rapid change in cross-section. Okay? So in this shaft, and in this portion of the shaft, I'll mesh really fairly large, so the thing will compute quickly. But in this area here with the radius, as you can see here and here, I've tightened my mesh up significantly. So I've selectively reduced my mesh so I can pick up that stress concentration. If I didn't do that, I might not even see that. It might show blue fading into green, and I wouldn't get the stress concentrator that I see there. Okay. So what's the lesson for today?
Don't build an airplane with square windows.
Exactly. That's
and
good.
use blue.
Use blue, yeah. But it is sort of amazing if you think about it. That's how they figured that out. Don't use square windows in airplanes. It was a catastrophic company-ending failures. You know, I mean, people don't like airplanes that fall out of the sky, and that's actually what happened. So, yeah, we can sort of run through this quick. I don't remember what this video was. Let's watch it. Oh, this was more circle. Did you guys do this already?
Yeah.
All right, we're not going to do this. It's in the notes. You can look at it. I didn't, you know, be honest with you, I had not done a Morse circle since college. And so I found this video, this guy does a really good job of explaining it. So if you don't remember it, you should at least be aware of what it does. I'd recommend you go ahead and look at it. But we won't do it in class. It's not really that valuable in a practical sense anymore, but it's definitely worth knowing about. So instead, we'll look at finite element analysis. And this is one of the reasons why solid modeling is such an important thing today, okay? Solid modeling, even today, where the modelers are pretty good and it's pretty fast, I would venture a guess that you could probably, if you were good in AutoCAD, still draw something with an orthogonal 3-view kind of drawing faster than you could model it. Maybe not, but I think you'd be pretty close. So you say then, well, why do we do solid modeling? Even if it takes longer. The reason you do solid modeling, even if it takes longer, is that I've got the capability to do things with that model, right? I can take that model and I can post-process it into a CNC program, right? So I don't have to sit there and write a G-code program. And the other huge thing I can do is I can analyze it. And I can do finite element analysis on it to determine my stress levels and my strain levels. And I can also do other analysis on it. I can do fatigue analysis, which I couldn't do even a couple years ago. That's fairly new to FEA. I can do fatigue analysis. I can do thermal analysis. I can take, for example, say I've got a machine frame that's going to operate outside. And part of it is shielded from the sun by a structure, but part of it's not. And say I'm going to run this thing in the desert. Well, I can not only put my mechanical loads, impart them onto my model. I can put the thermal stresses that are going to be created by having one end of the thing in the sun, and it's going to get up to some temperature, 100 degrees or whatever. The other end's in the shade, or maybe it's even cooled, it's in a building. I can model that thermal stress, and I can combine those stresses so I can determine the total stress on the structure, not only from the mechanical loading, but also from the thermal gradient that I've got on it. So it's a huge thing, and if solid modeling takes longer, the benefits that you get are just absolutely enormous. So that's my pitch. I don't sell solid modelers, but if I did, I'd probably be a pretty good salesman. But that's really the issue. That's where the real benefit comes from. And then you take that and you take it even a step further and you say, well, what if I have a design change? Again, I can do all that analysis. I can do my G-code programming with post-processing, even if I made a design change. So looking forward in a design, if it's likely, or even if you don't anticipate making changes, that ability is there to do things with. The other thing, even in the design process, I can do multiple iterations with the FEA. Like say I do my design, and I wind up with a stress concentrator where there's a sharp corner, or a notch, or some feature that's creating a stress concentration. I can do multiple iterations to find out what can I do in my design to minimize that. So again, solid modeling is huge. It used to be separate steps. You do a finite element, you do a solid model, then you would have to sort of remodel the thing in an FEA package. Then you would have a mesher, and then you would have a solver. There are actually 3 separate steps when FEA first even sort of came into the realm. And today you're in SolidWorks and you're just flipping between screens and making those changes, and all your analysis updates itself automatically. So it's a fantastic tool, unbelievable tool. Actually, this is wrong to a degree today. When I wrote this, we were using a modeler attached to Inventor, and I forget who did that model, whose modeler they were using then. Yeah, I'll come back to it. It doesn't really matter, but it was just a linear FEA package. Had no fatigue, had no ability to get into the plastic range. And again, we talked about stress strain curves. So, I mean, this is where we want to be in our design, obviously, right? We want to be below the yield point, well below the yield point, otherwise we risk deformation. But the point is, it's nice to have a FEA modeler that can deal with the plastic region as well. And the modeler we use today with SolidWorks can do that. And again, also deals with fatigue. So we can get up into the elastic range. Or up into the plastic range, okay? So I gotta erase that from my lecture, because that's from the first time I taught it. We made that switch to SolidWorks last year. But in any event, this portion of it's still good. The finite element method, again, you're modeling, you're basically taking your model and you're breaking it up into, you're meshing it, breaking it up into a bunch of nodes, and then the software runs the mathematical equations like we used, previously in this lecture that we went over very quickly, are formulated for each of those finite elements. and then and all those elements that are or all those values that are essentially pulled back together to create a system solution. So it's just an incredibly powerful tool, and the beauty of it is, I mean, even not that long ago, maybe 6-7 years ago, maybe a little bit more than that, 2007, 2008. Hold on one second here. There we go. You could not really run FEA on an affordable laptop computer. It was running on a really high-end, not really a mainframe, but a much higher-end computer than you can today. But today, the packages are so powerful, and ability to do things like selective meshing. So if I've got it, like I showed you on that shaft, if I've got an area that I anticipate having a higher than average stress concentration, I can selectively model or mesh that tighter and wind up with an accurate solution. So again, that's really fairly recent that's happened. That you can take a laptop that's sort of a standard engineering grade laptop and do some fairly sophisticated stress analysis on that. So fairly new thing. Yeah, I mean, so Inventor uses, as does SolidWorks, use the tetrahedral elements. I need to update this because we've got a different mesher now and a different solver. So again, this, the standard analysis, we're sort of showing the stress, the average nominal stress would be the cross-sectional area, right, about the loading. So this would be a calculation of that. But that's not really the big issue. The big issue is my stress concentration factor. And this is one of the charts I mentioned earlier. You'll find this in Rourke's. You'll find a little picture just like that in fact, that's probably where I pulled it from, of a plate with a hole in it. And what the stress concentration factor, what happens to that stress concentration factor as my ratio of the hole diameter to the plate width changes, right? So the smaller the hole gets, effectively, if you look at this, right? If you keep the plate width constant, the smaller you make that hole diameter, the bigger my stress concentration factor, okay? This isn't an especially bad shape, okay? But it still has that impact of having a stress concentration factor that's not insignificant. Okay. So, but there's I'll pull in, I'll bring in I have a copy of Works, I'll bring it in. You can just sort of look through it. Again, today, it's not something you're probably going to do. You're probably going to do the FEA, but it gives you some idea. It's useful just from a geometrical standpoint to look through it and see what some of the worst, shapes typically can be. A hole not being a terrible one, especially if it's a reasonable size hole. Smaller the hole, the worse the factor, worse the impact is. And that basically is what your maximum stress is. So if you've got a K that's high against your nominal stress, and this would be the calculation, right? We calculated our nominal stress back here, which was again just our load divided by our area. And then we, in the old days maybe, or even still today, I guess, you'd go to Rourke's or one of the other handbooks. You'd find a shape, or you'd find a shape that closely mimicked or exactly was your condition, find your stress concentration factor, and then determine your maximum stress from it. Okay, so if that exceeded, in this case it doesn't, it's only 2,000 psi, but if that exceeded your yield strength, then you've got a reasonably good chance of creating, or especially if it exceeds the ultimate strength, then you're for sure going to get it. But you have a reasonable chance of getting some issues with fatigue. So again, this was just another example, again using the plate, and then we did it in FEA. And you can see the loading, and again the stress concentrations at the bottom of the hole. Bottom and top of the hole, if you And this is with a pretty coarse mesh too. This was, I think I did this in Inventor, which I forget which package was embedded in that, but it wasn't nowhere near as good as the one in SolidWorks. And just some other conditions that we'll also look at. This is a deformed state. That's why the holes are sort of overlapping each other, but you see the stress level. This was actually multiple holes, so you had stress levels in it's actually 3 holes together, which was an even worse condition. Okay, that's okay. So next time we'll get in a little bit more into fatigue and loading, and I'll bring my other laptop, which I've got SolidWorks on, and we'll just play around with it a little bit and do some fatigue stuff as well. So, okay, that's it for today.